So, zeros of polynomial zeros. Zeros of polynomial functions. So, last time we talked about how x to the 6th power, well, that exponent would be the max number of zeros. We could have at most 6 zeros, right, at most. So, for instance, these zeros could look like maybe like 3, -2, 1/2, 1.7, I don't know, 5/20, 1/3. Those could be my 6 zeros because I'm only looking at the leading term because the term with the highest exponent tells you the maximum number of zeros, maximum number of intercepts that you can have. Your zeros could also look like this, plus or minus √3, plus or minus √5, I don't know, plus or minus 6, maybe √6 only. So we're looking at polynomial functions. A polynomial function of degree n can have at most n real zeros, either rational or irrational. So the top are all rational numbers. Rational can be written as ratios. Irrational, the decimals go on forever. So irrational numbers, more or less, maybe I should write that. Irrational numbers are pi, e, the exponential, and anytime you have a number under a square root, that's not a perfect square. So 9 is a perfect square. So if you have √9, that's equal to 3. But √8, that's not a perfect square. That would be irrational. So zeros can be rational or irrational. This is exactly what I just talked about. Rational, written as a ratio, irrational, root. So the rational zero theorem provides a way to determine a list of all the possible rational zeros of a function. Do you remember the P over Q? Maybe? No? Yeah, it's fine. If you do, great. If you don't, no worries. So, if a polynomial function is of the form, oh my gosh, it looks worse than what it is. This is just standing for a polynomial function. We went over this before, right? A to the n, this is just the first coefficient. It's the coefficient that's in front of the highest exponent. Oh, and then a to the n minus 1 is just, your coefficient that's in front of the second highest exponent. Not too bad. So if we have a polynomial function, and keep in mind the degree is greater than 1, so the highest exponent is greater than 1, we have integer coefficients, and a0 is not equal to 0, so we actually have a constant, a number. So maybe plus 5, plus 2 at the end. It's not just x squared plus x, right? We're ending with a constant number. Then every rational zero has the form p over q. So, I'm just going to warn you, sometimes the list is really long, so maybe I should write that for you. We end up making a list of all the possible zeros, and then it's just a process elimination. Because if you look at a really long polynomial, you're like, I have no idea what the integer roots could be. I'm sorry, what the x-intercept could be. But you have like infinity number of choices. Versus if I have a list, it's a lot easier. Okay, well, I know I have to have a positive root, so you can eliminate all the negative ones in our list. Okay, so sometimes the list is really long. Okay, do you have a question? I don't know, you three, hooligans. Okay. So, P and Q have no common factor other than 1. Well, that makes sense, because if it has a common factor, you can simplify, so it has to be fully simplified. P is the integer factor of the constant term A0. So, P is the integer factor of the constant term, and then Q is the integer factor of the leading coefficient. Cool. So, we'll just come down here and we'll talk about it. So, let's identify what P is in this polynomial function. You may recognize it. It's the question I gave you. We're actually going to figure out what the possible rational zeros of the function are. So, P is the integer factor of the constant term. P is your constant. Q is the integer factor of the leading coefficient. So Q is the coefficient of your leading term. So, list all possible zeros of each function, then determine which, if any, are zeros. So Q, we'll write as plus or minus 1, because we have to list out all of the factors of 1, right? So Q is 1, but what are all the factors of 1? 1 and negative 1. P is 4, so we have to list out all the factors of 4. All the numbers that add and multiply, or that multiply to 4. Positive minus 1, positive minus 2, positive minus 4. All right, so we're listing out all the factors. 1 and 4, negative 1, negative 4. Okay, and then, right, P over Q is a rational zero theorem. If I take every factor of P and divide by every factor of Q, right, it's like combinations. Remember in like 5th grade when you have 4 shirts and 2 pairs of pants, how many combos do you have? Right, so we're going to have a lot of combos here. So I'm going to take P over Q. So every factor of P over every factor of Q. So every factor of P plus or minus 1 over plus or minus 1, plus or minus 2 over plus or minus 1, plus or minus 4 over plus or minus 1. Oh, we only have one like thing of Q, so I could just write it that way. Oh, we're dividing by 1. Oh, it just is itself. Plus or minus 1, plus or minus 2, and plus or minus 4. So there's 6 options. 6 options. We could have maybe negative 1 is a root, maybe positive 1 was the root, maybe negative 2 was the root, maybe it was positive 2, maybe it was negative 4, maybe it was positive 4. So this is good, right? I asked you to find all the rational zeros of the function. Well, okay, let's say I was asking you to factor this original polynomial. Like you have no idea where to start, right? Because this is a cube function and there's not an x, there's not a common factor to pull out. So what you would have to do is like guess and check. Is it maybe 1 is the root, so you could try that. Maybe 5, you know, but you have to do the guess and check. This gives you an educated guessing options. So you really only have 6 options. You have 6 options to choose from. Okay, let's say we can try x equals 1, right? We're going to test. We'll pick one of our 6 options, plus 1, minus 1, plus 2, minus 2, plus 4, minus 4, right? We have 6 options. At least one of them, right? One of them should be a root. So we just got to try. I'm going to test x equals 1. I'm going to see if this is a root. How can I test it? How do I know? What is it? Do we have a way of figuring out?
Synthetic division.
Bingo! Synthetic division. That's a very easy way to see if something's a factor, right? We do synthetic division. If our remainder is 0, it's a factor. We're golden. So I'm going to test x equals 1. So I put 1 here. Right, so I have 1 as the coefficient of our 3, negative 2, 4, and then just synthetic, negative 2, negative 4. Oh, it goes evenly. What? So since this worked, that means x minus 1 is a factor. So that means x minus 1 is a factor.
Do we have to do this for all?
Because x equals 1. So since this worked out, I am going to have it fully factored. So this is x squared minus 2x minus 4. Then bring it down, the fully factored form. Oh my god, my handwriting is just getting worse every day. I don't know what's going on. So can I, don't say this out loud, okay? Think in your head. This left, quadratic. Can I factor it anymore? Can I factor this anymore? X squared minus 2x minus 4?
Yes.
No, because what multiplies negative 4 and adds to negative 2? Like if you have negative 2 and positive 2, it adds a 0. Negative 4 plus 1 is negative 3. So this is an irreducible quadratic. Technically it's prime. We can't factor it anymore as 2 polynomial functions. So that's it. This would be the fully factored form. So that's it. So the only rational zero we have is x equals 1. That's the only real intercept we're going to have.
So the answer is x equals 1.
So it wants us to list all the possible rational zeros, then determine which of any are zeros. So this was listing them, and this is the actual zero. Yeah.
So you don't have to test anymore?
Nope. Because I already, since x equals 0 went evenly, I like reduced it, right? I already took out that factor. And what I found, x squared minus 2x minus 4, we have to use quadratic equation for that. So it's not going to be a whole number. It's not going to be, the rest of them. So these are all the possible ones. You're always going to have a bunch that are like not actually part of it. Yep.
If like the result could be factored,
Then you factor it.
then that would give you the other answers.
Yeah, then we could see if more of our rational zeros were actually part of our answer. So that's exactly what we're going to do this time. Right, so this is exactly what's going to happen in part B. Perfect, leading us up to it. Can I scroll down a little? Okay, so we're doing the same thing. So we have P, we have Q, and then we're going to try to find the combinations of all the possible P over Q. And then we'll pick one number, we'll test it. If it doesn't go evenly, pick another number, test it. So ideally, we want to like reduce the exponent, right? We want to find at least one factor where we can move our polynomial we're worried about from a cube to a square, because you definitely can do quadratics. You're fine with quadratics. So this is my Q. This is my P. P is pretty boring. It's just a number, right? Q is, I don't have a good one. I don't know. Q is quite lovely. It's the number in front of your leading coefficient. I don't know. I don't have a good way of remembering it. Okay, so now let's list out all the factors of my P and Q. So Q, let's see, what multiplies to 2? 1 and 2, and -1 and -2. So plus or minus 1, plus or minus 2 are my two factors for Q. P is 15, so I have to list out all the numbers that would multiply to 15. Right? 1 and 15, -1, -15, +3 and +5, -3, -5. Right? So I have them all included. By writing plus or minus, it takes into account. Ooh, now we get to write that list, the P over Q. So first, I'll use my plus or minus 1 as my Q, right? If I'm dividing by 1, I'll have all the same answers, so I'm just going to copy down all of the P's. Sorry, let me make sure I'm not going too fast and skipping things. Does it make sense why I just like copied those down first? Right, my first factor is 1. If I go through, divide these all by 1, it's the same numbers. But now I go through and have to divide all these by 2. So I'm going to have a bunch of fractions. It's fine. These are rational roots. Rational can be written as ratios. So I have, let's see, plus or minus 1 over 2, plus or minus 3 over 2, plus or minus 5 over 2, plus or minus 15 over 2. Yes, you do. Yes, you do. Because the cool thing is maybe, okay, not cool thing, useful thing. Later, if we're like, oh, you know what? All of our roots have to be negative, that eliminates half of your possible, because then you take away the positive. Okay, so
Is there like any trick for this part to figure out what to plug in, or do you just have to guess and check off?
a lot of times I like trying 1. That's always a really quick one because it's very easy synthetic. And like, I don't know, maybe half the times that I've ever done it, it works. It's very quick synthetically. I like doing the integers first because I can do synthetic very fast with them. Because all I have to do, I just have to find one that works. That will take me from a cube to a square, because once I hit a square root, like, we're good. Yeah. So that being said, okay. Do we want to try, so I just said I like trying the integers. Do you want to try 1, 3, 5, or 15? I don't want to try 15 first. That's multiplying by a big number. 1, 3, or 5? Eeny, meeny, Daniel, what do you want to try, 1, 3, or 5?
1.
1. Okay, let's try 1. Let's see if it works, okay? So I'll try 1. If it goes evenly, I should have a remainder. I should have no remainder, and it should be good. So I have 2, -5, -28, and 15. Bring down the 2 to, let's see, -3. Ooh, uh-oh, this looks like we're in big trouble. It doesn't go evenly. Doesn't go evenly. Not a factor. Okay, let's try again. Ethan, 3 or 5? What do you want to do? 5 it is. Okay, indecision. All right, let's try this now. All right, bring down the 2, 10, 5, 25, negative 3. It goes evenly. Okay.
Can we not be able to check the negative?
What do you mean?
Negative, like, would you?
I'll go through that, like, second, yeah. I mean, okay. I was gonna say, like, I'm lazy. I try to do the easy stuff first, but I guess it's not lazy because I'd have to end up going back there anyway, yeah?
Could there be, like, are there other possible numbers that work?
These are the only rational.
Like, no, like, if I did, like, -3.
Oh, you could try -3.
So, like, would I only have to write -3, or would I?
Oh, so do you want to try that next, or be good? If you try -3, it goes evenly.
I did it anyway.
Yeah, it goes evenly, and then you end up with a quadratic. Can you factor the quadratic?
But I wouldn't have to do it.
Well, when you factor the quadratic, you end up with. So you see how I have numbers right here? I'm going to write them. I'll write them as 2x squared plus 5x minus 3. So that's the factor I'm left with. All right, since this works, I know x minus 5 is a factor because I got from this guy right here. That's where the positive 5. So if we have a rational root, it has to be on this list. Okay, what?
There can be, like, multiple.
Yeah. But if you look at, okay, so if I take this this cubic function, any of the roots that are rational has to be on this list. There's not a rational number that'd be a root that is not on this list.
So that, like, reduce.
So if I can factor this guy, that'd be great. All right, 2x squared plus 5x minus 3. Does this factor, or is it irreducible? Okay, what's a factor 2? Did we know?
X plus 3.
2x minus 1, x plus 3? Yeah? Okay. So I'm sorry, this is going all over the place. Let me be a little more clear. So what this means is one of my roots is a half, another is -3, and then the last one is 5. So all 3 of my roots, because remember this is a cube function, at most we can have 3 zeros, but all of our zeros are rational numbers. They are all on our list, right? Here's the positive a half, here's the -3, here's the positive 5. They're all on our list. Cool. Okay, so note, right? I tried 1, it didn't work. I tried 5, it worked, and then I could like keep going. All you have to do is like just find one magic key, and then you're like set, right? Ellie went through and tried -3 first, and then guess what? She ended up with the same answer as us. So if you would have tried 1/2, like those are the 3 magic keys to get in the kingdom of answers, right? I think we'll go on. Don't take too much time with this. Your favorite thing, Descartes. Descartes, rule of signs. That's why I was being facetious and saying it was your favorite thing. It's not. I know it's not. Okay. Let me pause this. So, ready? You count Descartes. This rule gives us information on the number of positive and negative real zeros. So, with the rational zero theorem and Descartes, you can actually figure things out. If Descartes says there's no negative roots, then you can actually cross out all the negatives from up here, right? So using these two in conjunction, it makes factoring a little easier. Cool. Okay, how do you do it? The number of positive real zeros is equal to number of variations of sign in the plus and minus signs of just regular f of x, or less that by some even number. Okay, so instead of like talking in generals, let's just go through the example. So the number of positive zeros. What you do is you look for the number of sign changes. I'm positive. Ooh, I turn negative. I stay negative. Ooh, I turn positive again, and then that's it. I only have 2 actual sign changes, so it's Vanna White time. Ready? Ooh, look here. positive. Oh, switch to negative, negative, switch to positive, stay positive. 2 sign changes. That's it. What?
I was like,
Is Vanna white? Yeah. Yeah, it is. Okay, so number of positive zeros, 2. But remember, star, star, less that by some even number. So you find your number, you subtract 2, and you keep doing that until you reach your 2 endpoints, 0 or 1.
why zero?
So however many changes you have to keep subtracting 2 until you reach 0 or 1 as your endpoint. So if I find 3 changes, subtract 2, I have 1. That's where you end. If I only counted 1 sign change, I'm done. Because, right? You always, what Descartes is, okay, count, and then you just keep subtracting 2 to reach either 0 or 1. Just keep subtracting 0. Now, the number of negative zeros is the same as the number of variation in f of negative x. Oh my gosh. So, number of negative zeros. What you have to do is plug in negative x in for x. When I plug in negative x into x to the 4th, what is negative to the 4th power? Negative times negative times negative. Okay, a negative times itself an even number of times. The sign doesn't change. Versus, if I take a negative times itself 3 times, negative times negative times negative, 2 of them cancel out and I'm left with a negative. I don't know, this is kind of, I don't know, am I being vague? Or does this make sense? Hopefully this reasoning makes sense. Let me show you to it again. A negative number times negative times negative times negative, right? That's to the 4th power. Oh, these 2 cancel out and make each other positive. These 2 cancel out and make each other positive. That's why even if I put in negative x, the x to the 4th doesn't actually change the sign in front. Versus, if I put the negative in front, if I put the negative in for this term right here, I have negative 3 times a negative times itself 3 times. Oh, it turns into positive. If I put it inside, then if I put it inside an even exponent, the sign doesn't change. If I put it inside an odd exponent, the sign changes. So that's the trick. Number of positive zeros, go through and see your changes. Then, anytime you have an odd exponent, change the sign in front, and then go and count. So now I can come and count positive, positive to negative, negative, negative to positive. Oh, so I have 2. That's not an end. I have to keep subtracting 2 until I reach 1 or 0.
I don't get what you mean by keep subtracting 2.
So let's say I had 7 sign changes. So if I had 7 sign changes, subtract 2. I'm not at 0 or 1. Keep going. Not at 0 or 1. Keep going. Oh, no, I'm done.
And it's always 2 you subtract?
Yep. You always subtract 2.
So you need to write all the ones in between, like the 5.
Yep.
And what do the numbers mean?
So these are the possible number of real zeros. I could possibly have 2 real zeros, or I could have none. Positive. I could possibly have 2 negative zeros or none. And so the last thing we have to do is we make a little chart.
Why is it
Plus,
7?
minus, imaginary.
Why isn't the 7 negative?
Because there's no x to plug into.
Oh.
So I could have 2 or 0. I could have 2 or 0. So I'm showing all the different combos. Remember, you have 2 shirts and 2 pairs of pants. How many different combos can you wear to school? Well, you could have shirt 1, pant 1, shirt 1, pant 2, shirt 2, pant 1, shirt 2, pant 2. Right? There's 4 combos. 4 different combos we could have here. So we could have 2 positive zeros and 2 negative, or we could have 2 positive zeros and 0 negative. We could have 0 positive and 2 negative, or 0 positive and 0 negative. Right? There's 4 combos. Yeah.
Should we always just like double the amount? So like instead of writing just like 1, 2, just write 2, 2.
Where do you see 1, 2?
No, like since for like the positive zeros, it's 2 or 0, but you wrote 2, 2, 0, 0.
Oh, that's because I want to make sure, if I'm trying to count the combos, I don't want to have, okay, ready? 2 shirts and 2 pairs of pants. So I could have shirt 1 and pant 1. I don't want to say, oh, shirt 1 and pant 1 again. I gotta say shirt 1 and pant 2. Right? So the reason I wrote that is so that way I can have every combo, right? Both positive and negative have 2, or one has 0, one has 2, one has 0, the other has 2, or both have 0. So I'm trying to write all the combos. I don't want to like repeat the same combo. Or you can't wear the same clothes 2 days in a row. You gotta switch it up. Whatever. Okay. What else do I need to do? Oh, how many like zeros could I have? What's the maximum number of zeros I could have?
4.
How do you know? Who said this? Ta, how do you know?
It's a degree, the highest degree.
It's the highest degree. Okay, so when I add all these up, they should equal 4. And imaginary is your filler, right? So remember how they make hot dogs? There's like add random crap in there. That's the filler. Imaginary is the filler here for your hot dog, okay? The total has to be 4. You look how many imaginary and real positive and negative you have. So the first line, 2 plus 2, how many imaginary do I have? 0. How about the next line? 2, 2, and 4. These are all the possible combos we could have. Yeah, that's it. Cool. Yeah, Descartes. Let's try B. That's it. Let's try it. That's it. That's Descartes, right? It sounds dumb, but it's actually like, I don't know. It's not too hard. And I guess it's useful, with the rational zero theorem. If we say, if we say that there only can be like 2 positive, actually, rewind. So if we said, we can have 2 positive or we have 0 positive, and I find that I have 1 positive root, I know immediately I gotta have a second positive root. Yep.
Wait, so what if it's not a 2 or a 0 and it's just a 1?
So if you get a 1, that's where you end. So you just leave it as 1.
Just 1.
Yep. So let's try the next one. Yeah. Okay, let's do the positive first. Number of positive roots. Let's see how many. So we switch over. Negative, positive, 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 negative. So I have 2. Oh, did I miss one? Yeah, right here. 3. I have 3 switches. So the possible number of positive zeros, 3. But remember, we gotta just keep subtracting to either reach 0 or 1. So 3 minus 2 is, keep subtracting 2 to reach 0, 1. And if I want to know the number of negative, you go through, and every time you have an odd exponent, you change the sign in front of it. That's the shortcut way. So it turns out we only have 1. Oh, and so I already reached my end. I don't have to subtract 2. I'm already at the end point, right? How many total zeros can I have? 4, right? Because that's my highest exponent. So I could have 3 positive and 1 negative, or I could have 1 positive, 1 negative. Makes it much shorter. Alright, because I negative, 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 positive, 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 positive. There's only 1 sign change. Alright, how do we feel about this? Alright. Yeah. Confused? Well, there's some practice coming up. Yep.
Do you want us to draw the chart?
Yeah. Draw the chart. That would be the quickest way. It's the easiest way for me to grade. So, complex zeros. The fundamental theorem of calculus says a polynomial of degree n, as long as it's greater than 0, has at least 1 0, real or imaginary, in the complex number system. So this leads to the linear factorization theorem, which states a polynomial function of degree n has n linear factors. So, for example, if I have something like, I don't know, to the 5th degree, right? That means it has to have 5 zeros. Oh, I did that. 5 zeros. So that means I have to have 1, 2, 3, 4. I have to have 5 factors. Now, not all of my factors are going to be real. Some of them might be imaginary, right? Thank you, Descartes, telling us some of them might be imaginary. But I'll always have like 5 factors. So that's the linear factorization theorem. A function has complex zeros when its don't want to say that. You can write it as 5 factors, but some of your factors may be imaginary. So when we do the quadratic formula, especially for the irreducible one, like this one right here, if I would use the quadratic formula, I would find 2 imaginary roots. Well, I could technically write them as 2 linear factors, but they have plus and minus i's. Okay, So a function has complex zeros when its factored form has a quadratic factor which has no real solution. Okay, this is called an irreducible quadratic factor. So an example, I could have x squared plus 9. This is irreducible quadratic factor, right? It's not a difference of squares. You have to use quadratic formula, or if you go through and solve, you see x is plus or minus 3i. Right, because you set, let me like rewind a second. You set x squared plus 9 equal to 0. You solve for x squared, you square root both sides. Square root of 9 is just the same thing as saying square root 9 times square root negative 1. Oh, that's just going to be plus or minus 3i. Okay, so it's an irreducible quadratic factor because you won't have real roots. Right, so we'll end up having a complex root. Hopefully this is a little review. So complex root is something like a plus bi. A is your real component. Bi is your imaginary. Right, so if I have a complex root, the bi is your imaginary because that's the part that has your imaginary number in it. So if I wanted to write x squared plus 9 as two linear factors, I would say x plus 3i, x minus 3i. Okay, so that gets us to this example. Right, we're going to put it all together. Oh my gosh, we're going to put it all together. So, consider this. Are we okay? I just hear like collective groans. Okay. Consider this polynomial, write it as a product of linear and irreducible quadratic factors. So, the first thing we're going to do is list out all the possible rational roots. Yeah. So, this is my Q, this is my P. I'm not joking. Okay. So, list it all out. So since Q is plus or minus 1, right, because Q is 1, that's the coefficient. The only factors for 1 are positive 1, negative 1. So all I have to do is list out all the factors of 24. Yeah, I know. This is a fun quiz, right? Okay. So the idea is we want to keep doing synthetic, just pick problems, pick numbers, do synthetic until the remainder is 0, and then we'll know that that's a coefficient. Yeah. I'll go with Ellie's number from before. Let's do -3 first. So try doing the synthetic. Ah, it goes evenly. So that means x plus 3 is a factor.
How did you know that was going to go evenly?
Because we have not much time in class and I picked one that goes evenly instead of letting you struggle.
But how did you know that that was going to be the way?
Trial and error. I was going to have people like choose random ones till we found one and then just keep going.
No, but how did you know without like doing the answers?
Oh, I went through the answers before.
Oh.
I've taught this class before. I write myself little notes, especially sometimes I'll like star things and like write it on my paper to make sure what I say to you. Yeah. So it's mostly for like academic language for the math, like what the heck is rational mean, like making sure you understand rational means ratio of two things. Yeah. Okay, so that's a factor. We want to keep going. We want to fully factor it, keep going till our remainder is 0. Because we start with an x to the 5th. Here, this is going to be an x to the 4th. Whatever. In the famous words, I don't know. Lil Yachty, YOLO. Let's do this. Let's keep going. Keep going. Keep going. Just got to keep synthetic till the remainder is 0.
So when we do synthetic now,
Didn't he say it? It was him.
Everyone says you.
I know.
Wait, when we do synthetic now, do we use that bottom?
Yes, yes. Use these same coefficients. Use these same coefficients. So I have negative, I'm going to try negative 2 next.
Oh, so we don't plug in the same number?
You don't want to plug in the same number. Nope.
Wait, why do you
We want to keep going till our remainder is 0 so I can have it fully factored.
Wait, so we're at this.
I knew x plus 3 was a factor, but now I'm left with an x to the 4th, blah, blah, blah. Yeah, so we got to keep going. Okay.
We have to do these for all of them.
You got to keep going. You got to keep doing synthetic till the remainder is 0. Synthetic until remainder is 0. Keep going. Ah, yes, it goes evenly. That means x plus 2 is a factor. Score. Okay. Then we want to use these same factors. Because now this is an x cubed term, right? To third, second, first, constant. Okay, we have a cubed term. You still don't know how to factor that. So we got to keep going. Use the same coefficients. Right? Because technically this is next to the 4th. Nah, we got to keep going. Technically this is next to the 3rd. Got to keep going. Let's see. Let's do 4. Use the coefficients we just did. Goes evenly.
Oh my gosh.
So that means this is an x squared term. Ah, we can deal with quadratics. Let's write this out and see what it is. Ooh, x squared plus 1. That's an irreducible quadratic factor because if it was x squared minus 1, it would be a difference of squares, but this is plus 1, so it tells you imaginary. This is an irreducible. It means we can't go further. We got to stop. Irreducible quadratic term. If it was x squared minus 1, it'd be a difference of squares. Because there's no number that multiplies to 1, positive 1, and adds to 0. Technically, it would be x minus I, x plus I. But we want to write it as an irreducible quadratic term. So, write it as a product of linear and irreducible quadratic terms. X plus 3, x plus 2, x squared plus 1. That is the answer to this guy.
Not x
You're
minus
also
4.
x minus 4.
Yep, x minus 4, my bad. Forgot to write that right here. So this is the x minus 4. Ay, ay, ay. And then b, but wait, we're supposed to write it as a product of linear factors. So I'm all good except for this last one, the x squared plus 1. How could I make this into a linear factor? How do I convert x squared plus 1 into a linear factor? Set it equal to 0. Because I want it as linear factors. Right now, I have a quadratic term. I want to split that quadratic into linear factors. So I'm going to keep my x minus 4, my x plus 3, my x plus 2. But the difference is I'll have an x minus I and an x plus I. Because technically, these are equal to x squared plus 1.
So E is plus or minus 5?
I? Yeah, I is plus or minus. Wait, what?
Number E is
B.
plus minus 5. That's the answer.
No, it's the stuff I highlighted.
What's
This.
the answer for X?
So notice that this has a quadratic term, and this, yeah, has it linear. A doesn't want imaginary. You gotta leave it as quadratic. B is asking for, hey, write it all in terms of lines, use I's, that's fine. And then C, I mean, you're just listing all the zeros. Negative I and positive I. So all the zeros, you just set all these equal to 0. Set all the factors equal to 0. Okay, so we didn't finish all the notes, but tomorrow it should be pretty quick. Okay.